One of the things I really like about doing mechanistic interpretability research is it's just so clean. You can
Mm.
just look at all of the internals, you can intervene on any given neuron. It's amazing.
Yeah.
I do not want to be a neuroscientist.
Yes. It is both physically and intellectually cleaner. There is no need to learn hand washing protocols as a mechanistic interpretability researcher for transformers.
This is a walkthrough of in-context learning and induction heads. Maybe beginning with introductions. I'm Neil. I'm currently an independent researcher in mechanistic interpretability, and I used to work with Chris Olah at Anthropic on this stuff, and was an author on this paper. And I'm excited to come share some takes on it. Charles?
I'm Charles. I am a deep learning educator working with full stack deep learning. Did my PhD studying optimization of neural networks and have been a big fan of this long thread of research on mechanistic interpretability and sort of peering inside neural networks. Started in neuroscience, wanted to understand how brains work, gave up on that, and feel like I can maybe learn something about how these artificial brains work.
Awesome. And yeah, we're going to try out the format where rather than just me monologuing, I try explaining things to Charles, and he gets to push back whenever I explain things terribly or go on long, meaningless tangents. So we're going to begin with just some high-level discussion about why does this paper exist? Why is this interesting? Why might you care about it? And so fundamentally, this is a paper about mechanistic interpretability, which is actually reverse engineering models that have learned to be good at a task, reverse engineering their weights into what are the actual algorithms the model has learned. As a pithy way to describe why I care about this, it is just a fact about the world that we have systems like GPT-3, which are computer programs that can basically speak English at a human level. And I have no fucking clue how I would write a computer program that could speak English at a human level. And it's just a fact about the world that this is the case. And this deeply offends me. And the goal of my research is to solve this. But it also just seems like as models are becoming increasingly powerful and influential in the world, actually understanding them just seems really robustly useful in a ton of different ways.
Yeah, I totally agree. I think one of the things that, drew me into machine learning from where I started in biology and psychology was that it's really hard to measure what's going inside an animal that has learned to perform a task. If you think doing mechanistic interpretability on a transformer is hard, I challenge you to do some patch clamping or some calcium imaging. Now that we have computer programs that can tell me what's in an image or generate an image for me, it feels like, wow, we could learn so much about language, about images, and even about like algorithms in general from looking at what has been learned by these models.
One of the things I really like about doing mechanistic interpretability research is it's just so clean. You can just look at all of the internals, you can intervene on any given neuron. It's amazing.
Yeah.
I do not want to be a neuroscientist.
Yes, it is both physically and intellectually cleaner. There is no need to learn hand washing protocols as a mechanistic interpretability researcher for transformers.
So this is the paper about in-context learning and induction heads. So what is an induction head and what is in-context learning? An induction head is this small circuit that gets learned by transformers, where you have two attention heads in different layers that are cooperating to make this thing which learns to look for repeated sequences in the text and to continue. Concretely, if you give the model some sequence of random tokens like this, and then repeat it, the induction head can look arbitrarily far back in the text, look for copies of the current token, look at the thing that comes after the current token, and then predict that that's going to come next. This is, I don't know, a pretty sensible algorithm. Text often contains repeated strings. Looking for repeated strings is a pretty reasonable thing to do if you're trying to predict the next token. But it turns out induction heads are just wild and have loads of rich, interesting details. For example, they seem to be the main mechanism by which models do in-context learning, which is the other headline thing in this paper. In-context learning is where models learn to use text really, really far back in the context to predict the next token. And this is a kind of weird thing that models are capable of doing.
Mhm.
Like I could give GP3 like 1,000 words, and it's better at predicting the 1,000th word than it is at predicting the 100th word.
Mhm.
But like naively, if I'm running an algorithm for how you would use text to predict what's going to come next, it's really obvious how you could use like the current token, the last 5 tokens.
Mhm. Mhm.
I can kind of see how you'd use the previous sentence or previous paragraph. Like, how on earth do you use things 900 words back?
Mhm.
But empirically, transformers are just capable of this. And this is an interesting difference between transformers and earlier models. Here's a graph from scaling laws for neural language models. And here we've got a plot of how good models are at predicting a token, depending on how far it is in the context.
Mhm.
And the red line is an LSTM, which is an old language model architecture, and it totally plateaus at like 100. And transformers just keep going down up to like 1,000. That's just a really weird and impressive thing they can do. And one of the core claims in this paper is that the main reason models can do in context learning is because of inductions.
Got it.
And a lot of the papers are structured around like actually proving and showing that.
Mhm.
Making sense so far, Charles?
Yeah, definitely. And the core thing with in context learning is that this seems to be what has allowed these large language models to make a discontinuous leap from what previous models were capable of. That is, because of the capacity for in context learning, you can use the early parts of the context to set up what it is that you want the model to do, to set up the domain, to sort of adjust the behavior of the model. Like the less context you have and the less ability you have to learn from that context, the less controllable the model is, the less flexible, the fewer tasks that the model can perform. And so this is like an important phenomenon for understanding recent applications of these large models to things like code generation, to all the like really neat transformer tricks that people like Riley Goodside are sharing for being able to get them to do a wide variety of complex and useful tasks.
Yeah, one thing which is just really wild about GPT-3 that is not true of smaller language models is you can just give it a bunch of examples of some novel task, and then just it learns to get better at that task. If you give it 20 examples of solving an anagram, it is better at doing anagrams than if you don't give it anything, even though all of the model's parameters are just learned during training.
Right.
So this is like a distinction between a memorized algorithm the model just gets during training
Mhm.
and an inference time algorithm that the model runs on the text it's given
Yeah.
to like come up with some new algorithm or capability. And induction heads are just a really clean example of an in-context inference time algorithm.
Mhm.
I can give the model some random sequence of text it's never seen before, and it's able to predict the repeat of that later.
Right. Yeah. And there's hope that these kinds of inference time algorithms, at least components of them, might be something less data dependent, maybe even slightly less architecture dependent than some of the other features that models might learn or the facts that models memorize. These might be things that you would observe in models trained on code and not natural language, or models trained on a very different type of sequence data. It feels like the sort of thing that you would expect to observe, perhaps, in any model that needs in context learning, like a general algorithm.
Yeah, I mean, I'd expect you to see this in something like a decision transformer,
Mhm.
also a transformer doing some kind of reinforcement learning thing like Gato. You're probably going to repeat some moves or repeat
Right.
some sequences of moves. This idea of universality is a pretty deep theme in mechanistic interpretability. This idea that there are these algorithms or features or motifs that are there in kind of universally across similar models trained on different data sets with somewhat different architectures or different sizes or trained for different amounts of time. And this is like a thing that you really hope would be true, because if it's not true, you need to just start from scratch with every model. But one of the things I find really inspiring about this paper is that it just shows induction heads come up in every model they look at.
Mhm.
And I've looked at maybe 40 open source models, and all of them have induction heads.
No.
And it's this really deep, universal thing about how transformers model things. One thing I find particularly inspiring is it means that you can look at these really tiny toy models Like the way we discovered induction heads was by looking at a 2-layer attention-only transformer, which is this pathetically small, tiny thing. Yet we found this interesting circuit that just is there in like a 50 billion parameter model. I'm personally just really excited to see more work on toy models. Project which will hopefully be out by the time this video goes up is I've trained my own 1 to 4 layer tension only and full transformer models, including with this activation Anthropic found called Solo. And I will hopefully open source them along with the library I'm writing for doing mechanistic interpretability. And if you find this kind of stuff interesting, I would love to see what kind of thoughts you come up with.
Definitely the opportunity to switch from like a fundamentally naturalist way of looking at neural networks, right? Where you're just sort of like collecting phenomena that you've observed to sort of being able to predict future behavior or guide future behavior of models or development of architectures. That's a huge shift in the way that the field operates. Toy models, simple examples. The history of science is littered with cases where somebody accidentally stumbles upon the case where you can actually understand what's going on, be it finches in the Galapagos or gravitational lensing around the sun, where it's like, yes, this thing that would be really hard to observe in the system that we actually care about for relativity, that's satellites zooming around the Earth, for evolution, that's changes in ecosystems and biodiversity, really hard to observe in those places. But if we find the right smaller system and do detailed, thoughtful observation and even manipulation, then we can understand it and generalize it to those bigger systems.
Another thing that I find really inspiring about this is when I'm thinking about neural networks as an organism, there's kind of this really microscopic cellular level thing of you're looking at a neuron and saying, what does it mean? Or you're looking at a head or a small circuit and you're saying, what does it mean? And it's kind of the tiny building blocks that make it up. But then there's the big macroscopic thing. It's like, what is the loss curve? Does this thing learn? And a thing which I find really interesting and inspiring about this work is there's like a clear point in training that they call a phase transition, where models learn these induction heads. And if you look at the loss curves, there's this like small visible bump that happens. And a lot of what the paper is arguing is that this bump is when induction heads happen, they happen pretty suddenly, and they are the reason that this bump happens. And just the sheer fact that we can unify the equivalent of a small fact about cells to like a fact about animal behavior really suggests that reverse engineering small things can teach us deep, meaningful things about large models.
The analogy in the paper is drawn from a different scientific field, from physics, which is that we have detailed models of particles that we could in principle use to predict the behavior of boiling water, but is like a waste of compute to try and use the Schrodinger equation to predict when your water is going to boil, because there are much simpler laws that are available that are even linear that arise from looking at these things at a broader scale, at a coarser grain. And it just requires finding the right nonlinear transformations, the right lenses, the right things to look at so that you can understand that macroscopic behavior properly. And it feels like induction heads and in-context learning are among those lenses for these sequence models.
Yeah, just the fact that there are these like deep themes in the model that it learns. Like one thing I found really cool in this paper is they found that this core algorithm also seemed to be used in more sophisticated behavior. They have this head which can attend between different languages. Like it sees the word temple and it attends to the thing in English that came up with that. Or grand and largest. But the core algorithm seems to be the same as this induction head. And this head also shows the induction path. The final theme, which I find really interesting about this paper, is the fact that it's interpreting models during training. Like we're not just looking at the model at the end of training as this final organism. We're looking at the induction heads during training and how they form, and getting this really striking observation that there's this dramatic phase change or phase transition where you go from no heads to heads in a pretty narrow band of training. And to me, this is kind of the difference between doing biology on an organism as is versus trying to understand the evolutionary history of how it got there. And there's just a lot of things you just can't understand without the evolutionary history, like that weird nerve in our necks that goes down to like our chest and back up again for
Yeah.
some random evolutionary reason.
The vagus nerve. Yeah. Yeah.
Vagus nerve.
Yes. Goes back to our fishy past. And if you think it's embarrassing that the human vagus nerve goes under the aortic arch, I challenge you to look up the vagus nerve in a giraffe or a brontosaurus. It's truly, you are lost. Vagus is wandering in Latin, and that's like a very apt term. Being able to observe the entire history of these models is an additional advantage for understanding them, on top of the fact that we can also, once you get a final model, probe it so thoroughly.
And yet, one sub thing of this looking at it during training is the fact that it has this phase transition. Yeah, like if you're looking at various metrics of how induction heads form, there's this very striking shift.
Mm-hmm.
And I think that phase transitions are just a thing where there is generally being a lot more interest and research in nowadays. That seems to be this pretty common occurrence. So my most recent project was researching grokking, where you got this very dramatic phase transition on small algorithmic tasks, where they went from totally overfitting to generalizing when they kept seeing the same data many times.
Yeah.
But there's also lots of other examples of this, like GPT-3 can do addition and a smaller version of GPT-3 can't. This is a somewhat different kind of phase transition because it's a phase transition in scale rather than a phase transition over training time. But given that smaller models trained for longer can be better than GPT-3, as we saw with Chinchilla, I think that these are kind of fairly continuous. Or another example I really liked was Tom McGrath from DeepMind had this fascinating paper reverse engineering bits of AlphaZero and its ability to play chess. And he found that it just pretty suddenly developed a lot of chess knowledge around step 20,000. It went from it can kind of figure out the opening game to like several rich concepts from human chess just appeared and were now legible inside the model. And one hypothesis, which I personally find really compelling and would love to see more research on, is this idea that actually most things models learn are these phase transitions, where for any given circuit within a model, like some capability or thing that it learns, there's a pretty sudden period of training where it goes from bad at it to good at it. And the smooth loss curves we see are actually just the sum of many small phase changes.
Yeah.
And just most capabilities are not a big enough deal that you see this bump in the loss curve.
Right.
So you don't really notice most of the time. And the kind of grandest version of this hypothesis would be that these big macroscopic ideas like scaling laws, that as you train the model for longer or make it bigger, loss smoothly changes, are actually just because there's lots of these small phase transitions adding up, and we have some law of larger numbers over the distribution of possible circuits that averages out to this really smooth thing in the limits. I don't know, there's just so many deep questions about learning and interpretability and training dynamics that this paper touches on.
Yeah.
Part of my personal interest in interpretability is I'm pretty interested in alignment. How is it that when we get systems at a human level and beyond, that we can make sure they're really doing what we want? And I really want to be able to look inside them and figure this out. And I think that understanding phase transitions might be pretty important here, because if models can suddenly figure out something like, do I want to do what my operators want, to be honest, versus tell them what they want to hear? That seems like a really important thing to know, versus they'll be really bad at telling us what we want to hear before they're very good at it. Right. You can intervene then.
One of the primary things that's been slowing down the adoption of these models in more contexts, self-driving cars, medicine, law, is the lack of mechanistic intervention. We have really great tools for mechanistic intervention in computer programs that are compiled from source code, and we don't have that for these models. And that things like the mesa optimization or sudden emergence of capabilities are very salient long-termist concern around deploying these models. But we see the same thing. I did some work on a ultrasound interpretation and guidance neural network, helping people take and interpret ultrasounds of people's chests. It worked super well, but it was very hard to tell what it was doing. And attempts to try and interpret what it was doing on the basis of things like integrated gradients or saliency maps and attributions were suggestive, but not compelling. And regulators of high stakes scenarios want to see compelling, not just suggestive. There's just a wide open field of applications where mechanistic interpretability enables engineering application in the same way that mechanistic interpretability of physical models of bridges enables the construction of larger and more useful bridges.
Yeah, and there's often so many subtle bugs in models. Like, models think that asthma makes respiratory diseases less lethal because you get better medical care if you have asthma because people are more concerned.
Right.
So it recommends you discharge them from hospital way earlier.
Right.
And just various things where it can get good performance, but for terrible reasons.
Mm-hmm.
Yeah, I really wish that just more people were working on mechanistic interpretability. It just seems so uncontroversially good from so many different perspectives. Like with my long-term alignment hat on, this seems great. If I want to make systems that are kind of fairer and more transparent, being able to look at it and see if it's actually reasoning about things like race or gender seem pretty important there. If I want to deploy it for code, law, and medicine. There's just so many fascinating questions.
Mm-hmm. Yeah. If I want to debug it, right? I've found that my model has made errors on this class of things. I've noticed a correlation between some feature of the input and some bad feature of the output. Like right now, the answer is, I don't know, train it again. And like compared to what we do when we detect bugs in our 1.0 software, it's examine the source code, reason about what the error is, do some empirical evaluation on inputs, and then resolve it. That's where you should hope to end up in software 2.0.
Yeah, one can but dream. But yeah, should we jump into the paper?
Yeah. Let's dive in and look at some of the arguments for this.
Also, briefly recapping core claims of this paper. There is this circuit called induction head. This shows up in many models, all models we've looked at, and seems to be pretty fundamental. There is this phase transition during training where models go from not having induction heads to having induction heads. This phase transition also has these other weird things, like models go from bad to good at in-context learning and have a bump in their loss curve. And the paper is arguing that these are all because of induction heads, and that induction heads are just this really deep, important to fundamental mechanism. And a lot of the paper is going through, in my opinion, slightly overly rigorous attempts to show that these are definitely happening. And I don't know, the 6 arguments, I was convinced by argument 2. Briefly outlining what these 6 arguments given are. There's macroscopic co-occurrence, which is this idea that there's just like, is this phase transition during training where models go from can't do in-context learning to can, don't have induction heads to do, and like, sure would be weird if this is just a coincidence, right? That would be so suspicious. Argument 2, we invented this kind of weird architecture we called the smeared key architecture that made it easier for models to form induction heads. And we found that one-layer transformers go from completely do not form induction heads because it requires 2 heads and 2 separate layers composing to can form induction heads. And it significantly boosts in-context learning, which is like a kind of very clever causal intervention.
Right. So to clarify, like argument 1 is fundamentally like a correlation argument, right? Yeah. And there could be a hidden cause, which is that at the same time as induction head circuits are forming, some other circuit is forming or some other feature of the model is changing in a way that allows for in-context learning, right? And then argument 2 is saying, at the very least in these attention-only models, we can make a targeted change to the architecture that, if this is a causal relationship, predictably changes that causal relationship, and then you observe the expected change.
Yes. Importantly, the change is designed to make induction heads specifically easier to form, yet also has this effect on in-context learning.
Right.
Argument 1 on its own, definitely not sufficient. There could totally be a third factor causing both of them, but I was convinced at this point in the paper. But the other arguments are cool in their own right. Direct ablation is this kind of dumb thing. If you just like delete a head, how does in-context learning change? And for the induction heads, it changes a lot. For the other ones, it doesn't change that much.
You said you were convinced by argument 2. I was convinced by argument 3. I wanted to see the ablation. I like to see a direct causal intervention. Maybe this is my neuroscience background. You know, from Phineas Gage on, we've been all about ablation in neuroscience. Chemical ablation, physical ablation, optical and electrical ablation are key ways that you dissect neural circuits in biological brains, as much as I loved the architectural intervention in argument 2, argument 3 really got me.
Yeah, I think argument 4 might be my personal favorite, which is that we can find these induction heads just based on whether they have this really basic repeated pattern behavior. But if you actually look at them on real text, some of these heads, which are fundamentally induction heads, are also doing much more sophisticated stuff that kind of seems to be at this more abstract notion of copies of the same token. For example, there are heads that can do induction between two languages, where the thing after an occurrence of the same token actually means the token after an occurrence of the current word in the other language, or few-shot learning, where it tends to the most similar examples of the current problem earlier in the context, even for really weird and novel tasks. To me, this is the strongest thing. This is a really deep mechanism of how models work in a way that is not at all obvious from this, that if A, B has happened and A happens again, token B will happen.
Right.
Which seems kind of trivial.
Right. The narrow definition of induction heads that you use to find them is based on this literal copying behavior. But that literal copying behavior, one can imagine implementing that in a program yourself. One can even imagine maybe writing the weights for some Markov skipgram model to do that kind of copying behavior. But then what's exciting about this is not just the literal copying behavior, but broader notions of induction that are based off of fuzzy matching. Argument 4 is looking and observing, not just observing these macroscopic things about in-context learning, but looking at concrete examples and saying, look, here's how this circuit is being used to implement this fuzzy match in these specific examples.
Yeah. Argument 5 is also pretty close to my heart. Mechanistic plausibility. Here, the argument is just literally, we can reverse engineer in a tiny model exactly how induction heads work and exactly why they must contribute to in-context learning. And conceptually, this mechanism seems like it could clearly generalize to translation and few-shot learning, which feels like pretty good evidence of it actually just makes sense that this could happen in real models. And hopefully at some point in the next few weeks, I will have a tutorial of how you can actually reverse engineer this yourself, because it's just not that hard. One of the things I really like about mechanistic interpretability, especially with toy models, is it's just not that hard to get results pretty quickly without needing a lot of compute or massive resources.
The primary limitation of argument 5 is that these mechanistic reverse compilations or reverse engineering, this is all done on these attention-only transformers that were originally developed in the mathematical framework paper in this transformer circuit series. They don't have MLPs in them, right? The transformers include these MLPs to do nonlinear transformations. And that is the part, that's the black box that prevents reverse compilation for larger and out there driving startups type models.
I think I want to push back a bit on that. So in this paper, we just focus on attention-only models.
Yeah.
But I've definitely played around with reverse engineering them in real models like GPT-2. And I've definitely played around with a 2-layer model with MLPs, and it wasn't that much harder. Larger models, it gets kind of messier, and you can't do it in quite as clean and naive a way. But I basically bet the same spirit of thing could work. And argument 6, I don't know, isn't really a real argument. It's just saying, for the previous 5, the case for small models is stronger than big ones. But it seems kind of plausible that all of the arguments generalize, given that some of them generalize pretty well. I'm not convinced either needs to be said, but it's an argument.
It's an argument. And I guess it does fit a little bit poorly with the phase transition component of the position of this paper. Maybe we should actually anticipate that things are not very smooth.
All right, let's jump in. Okay, so here they introduce a method they used that I thought was pretty cute, which is this idea of per token loss analysis. Ultimately, what we want to do is really dig into the guts of our model and look at its internals. But we're also trying to compare models across many different scales and to some degree different architectures. And so it's also useful to be able to think of them as just a black box function with an input and an output. And here the cute idea is just, let's give the model 10,000 random sequences of text and then pick out a single token in each of these and look at the model's loss on each of those tokens. Like, how good is it at predicting what that token is? And then just think of the model as being a map that takes these 10,000 input texts in and gives out a vector of 10,000 losses. And then let's just like compare these either over training or like between models.
Could I ask some questions about the per token loss
analysis? Yeah, go for it.
Thing? One thing that I found unintuitive about this was this like random sampling component of it where you pick random tokens to look at. It seems to me like, you know, you have loss on token from one sample for all tokens. Like, I get why you don't want to collapse it across the sequence dimension, because there's maybe like interesting information in how things are changing throughout the sequence dimension. So that I get. What I don't get is, why don't you just like take this big matrix and ravel it out into a vector of like, these are all the losses on every element of every sequence, as opposed to doing this random sampling thing? Is it like a computational efficiency thing primarily, or is there some actual benefit to the like random sampling?
Good question. The reason I think this actually matters, so in part, I don't expect it will change the results here, though I expect it will make things a bit messier and noisier. So the main problem is that within a text, different tokens within a text are very correlated compared to tokens between text. And if we're trying to study trends in overall model behavior across the distribution, you just kind of want to get rid of unnecessary additional correlation.
Right. You want the first eigenvectors to be the phenomenon of interest. And the first eigenvectors here might turn out to be things about correlations between nearby tokens rather than things about how the model is learning throughout a sequence.
Yeah, well, that's good. That's a good way of phrasing it. But we map each of the many model checkpoints across the many models to a 10,000 dimensional vector of losses. And then we try to apply dimensionality reduction to this. Like, what's an algorithm that can take this series of vectors and reduce it? And here we use principal component analysis. Pretty straightforward technique. It just says, what's a direction that kind of explains as much of the variance in these vectors as possible? Like, if I delete the component in the direction of this vector, the vectors get like as much smaller as possible. And then you just iteratively do that. So you remove the first component, then what's the next maximally explainy second component, etc. One thing I like about this technique, I don't actually know if it's original to this paper or not, is that it's just like a really general way to look for important trends as you change things about models, like as you increase model scale, as you increase model width, as you train a model. Generally, these principal components will just pick up on things.
Yeah. Definitely. I think principal components analysis is sort of the like basic dimensionality reduction, the thing that you should reach for first. And it's only after that that you'd want to reach for things that are more like complex dimensionality reduction, either like independent component analysis, which at least like reduces some of this like Gaussianity assumption and can find nonlinear interactions. And then moving on from there, things like UMAP and t-SNE and those kinds of algorithms that are a lot more hyperparameter sensitive can potentially uncover more complex features, but are also a lot harder to work with, a lot harder to interpret. So if you can find something with PCA, you should try and find it.
If you do a scatter plot of the first two principal components, you see this like very sharp bump where models swerve and then swerve again. And this bit highlighted in yellow corresponds to the period in training that we claim this phase change is happening in. And importantly, we only see it in 2-layer models and 3-layer and above, not 1-layer. Because 1-layers, they can't form a circuit containing an induction head because it involves composition.
Actually, I have a question. Do you happen to recall what the eigenvalues of those first two principal components were, like their magnitudes? Because like one thing I noticed is you mentioned in that description that the pivot is orthogonal. We go down and then we make a like 90-degree turn here. Orthogonality is very meaningful when we have these linear dimensionality reductions, right?
Yep, approximately.
But it's not like axis aligned, right? Like it's not that it's moving along one of the two principal components.
Yes. So I don't think whether it's axis aligned is that significant. Often what I found when I'm doing PCA on things is that if there's one thing that matters, another thing that matters, but say they're like a little bit correlated, like in the Grokking case, the memorization versus generalization thing, you actually tend to get a component that's like the difference between the two
Mm.
or something. Like it picks out on what matters, but it doesn't necessarily pick it out in an exactly axis-aligned way.
Yeah. I think what you'll find is that the closer the eigenvalues are of the principal components to each other, there's a degenerate case where there's a two-dimensional space in which you can plop two principal components in any orientation, and then axis alignment goes out the window. So it's only if the eigenvalues are well separated that you would expect there to actually be axis alignment for the thing that you're interested in.
Makes sense. Let's resume going in order. Now we're going to go through the various arguments. First argument, phase changes. There is this dramatic phase change during training when all of these different things we're claiming happen at the same time. This is something worth dwelling on. We make this claim that in-context learning abilities dramatically increase. But like, what does that actually mean? You can't make sexy graphs like this without a metric.
Right.
So the pretty janky metric we came up with, which I think it's somewhat reasonable to be skeptical about, is what is the loss at position 500 minus the loss at position 50, averaged across a bunch of data?
Yeah.
So long as your text documents are sufficiently chopped up and offset, so there's nothing special about the first bit, which is generally the case in the kind of training data we study here. It just begins at random offsets. This should be a pretty good proxy. I think it's also reasonable to be like, why did you do 50 and 500? This is so cherry-picked. And I think there's a bit in the appendix where we try a bunch of other versions. They all work about the same.
Right. A couple things. First, I think I buy the metric as a way of looking at it, because like, what does it mean to learn in context? It means that you're better later in the sequence. I'm actually kind of intrigued by this point about the chopping up of the data being important. So what this isn't is an attempt to look at performance on a bunch of tasks where we expect in-context learning to be important. Like you could say, oh, in-context learning is defined as the ability to do few-shot learning, right? That's how in the original GPT-3 paper, it's primarily defined in terms of few-shot performance, right? And it's like compare across model sizes, how good we are at these few-shot learning tasks.
Yeah, it's probably just worth double clicking on that and emphasizing that like this paper is deliberately taking a different definition of in-context learning to the GPT-3 paper. Like we mean the ability to use long context to predict the next token in general, not few-shot learning.
So these are like random portions of sliced up documents. So there's not anything special at the beginning versus the end. That's actually like quite different from the way people right now are using these models, which is there's a prompt and we want a completion of it. A very important distinction between the beginning of the sequence and later in the sequence. So I'm curious to what extent you see this definition of in-context learning as aligning or not aligning with in-context learning is what makes my prompt engineering work.
It's a good question. So just to flesh out my intuition of why chopping up text is important for model training, especially if you're using some kind of absolute positional embeddings, often models will pick up on some motifs that tend to occur at the start of a text. For example, if you look at the open web text data set, which is close to what GPT-2 is trained on, it has lots of news articles in it, which often begin with like CNN or Reuters in the third token position. And if you don't chop things up, it just learns, oh, my third positional embedding should have a CNN and Reuters direction. And that is not the kind of thing you want. On your more general point of how should we expect this to link up, I think I agree that it's like a bit of a jump. It would not be incredibly surprising if these just turn out to be different capabilities, though I would kind of expect this to be like a strictly harder capability than few-shot learning. I guess partially it depends on how much we think we're using these models in something that's out of the training distribution versus in the training distribution, where say few-shot learning is actually kind of weird. I feel like sometimes I'll see things with a bunch of repeated patterns, but I'm not sure I'll see, please solve the following problem. Here are 5 examples. Complete the 6th. That often. Outside of, I don't know, an IQ test or something. So in that sense, that is actually somewhat outside the data distribution. And you should always be kind of a bit hesitant and skeptical when you step outside the data distribution, because model generalization can be weird. And in some sense, we haven't at all constrained how the model should generalize. But it also just conceptually seems like, to the degree few-shot learning does come up in the data set, which it probably does, because otherwise, why would GPT-3 learn it? The ability to use far-back things to predict the next thing should include the ability to do few-shot learning in there. Though it could always be that that's 1% of the value of in-context learning, and induction heads are just not relevant for that part. Yeah. I don't know. One thing I'd be super interested in is, so I know GPT-J and GPT-Neo X have a bunch of snapshots available. To the degree they're capable of few-shot learning, just go and try them out on these different checkpoints, compare, and see if there's like a clear jump and whether the clear jump coincides with this induction bump or somewhere else in training. Seems like a really interesting concrete research question. I don't know if anyone's studied.
Yeah, one thing that might be useful is as people are coalescing around Hugging Face as the place where people share all these different kinds of artifacts around research, an in-context learning data set / evaluation might be helpful. Mostly people think of these evaluations as like, oh, this is how I can get my like glue values or my perplexity or whatever. And it's like very benchmarkist, but it doesn't have to be, right? It's like a very general way of setting up a consistent workflow that models can like hook up to that interface and then get that result. So it might be easier both for you and for other people interested in extending this work to something else to like do that part of that larger ecosystem.
Nice idea. One kind of free win I found in one of my current side projects, which is training a GPT-2 medium-sized model with softmax linear unit activations, was that kind of when you're calculating the loss, you calculate the log prob for the next token for every token, and then you average. Normally you average in the loss function. You can just return the log probs. And if you do that, you can calculate all of these metrics like in context learning for free.
Yeah.
And just add them to your logging code or weights and biases charts. And just looking at like, how did a model do on the first 8, 16, 32 versus 1,000 tokens? Or how does it do on the last 500 as additional metrics? Can be kind of interesting and cute.
Yeah.
And just like basically no extra computational costs because you're doing it all anyway.
Right. Yeah, maybe we can make a PR to torch metrics.
But yeah, I do like the Hugging Face idea. That seems not that hard to do. If you're interested in doing this kind of thing and watching this, reach out. I'd love to chat.
Yeah, my Twitter DMs are open.
So this graph is the loss by index, by like position. Normally loss is averaged across the context into just a single number, but you can just get a per token log prob, and you can average over just the batch dimension to get this vector. Here we look at up to 512. You can look further. And then this axis is the number of training tokens seen, which goes up to about 12 billion and is on a linear scale.
Yeah.
You can just plot that vector of length 512 for each snapshot into this pretty high resolution heat map.
Right.
I think we had something like 600 models in this. The like really striking thing we see is this pretty sharp jump. You see this pretty sharp transition around the point where the bump happens. The sharp transition just shows total loss goes down.
Yeah.
But if you look at the gradients, there's also this, well, it's kind of subtle, but I would argue that it fades a lot more as you go further down from this point on than here. So this graph is designed to make that like more viscerally obvious. So what we're plotting here is the derivative along this axis, the pairwise difference between elements of this vector. And what we see is, so white means basically constant, dark blue means significant change, and light blue means kind of some change. And so the fact that there's this very sharp line between white and light blue shows that it goes from flat to continuing to go down. And this corresponds to this vertical stripe, which corresponds to the bump in the loss curve. One cute thing while we're here is, in my opinion, there's also kind of like a second bump, like a second stripe here, that corresponds to like a very tiny bump here. Yeah. I have no fucking clue what's going on there. No. So if anyone wants to look into that, I would love to find out. Yeah, this is kind of reiterates my point of there's just so much interesting stuff in toy models yet to be discovered. And I would just love to see what anyone finds in my models. Even in two-layer models. Great. Yeah. This is how much the model gets better at learning within the context as like a much more fine-grained thing. You can kind of think of this as like an accompaniment to this really crude metric of 500 minus 50. That definitely is a robust thing here. Our janky metric is good enough. All right, so now we're going to shift a bit and we're going to get a bit more mechanistic. Everything up here was just, there is a phase change in context learning. But now we're going to try to tie this to induction heads. Really key thing about induction heads. Let me go find a picture. They have this really distinctive stripe down here. So this is a plot of the attention pattern.
Mhm.
Y-axis is the destination token. So here, number. X-axis is the like source token. So here, everything before number, previous tokens it could attend to.
Mhm.
Let's just focus on red for now. What we see is that on this induction head, it's attending to the thing immediately after copies of the previous token.
Right.
This is the first paragraph of Harry Potter because Chris likes Harry Potter.
I thought it was a bit of maybe an inside joke, which is that if you want to learn another language, a great way is to read the Harry Potter books because it starts off very simple and then the language gets more sophisticated over time. And I literally have a copy of the German version of Harry Potter und der Stein der Weisen on my desk right now for that purpose.
I'm pretty confident that was not intentional, but I love it, and that is now my headcanon. So here we've just got repeated the first paragraph of Harry Potter, and this is a specific head's attention pattern. And we see it's like very much what we'd expect from this continue repeated subsequences thing. It attends to the thing immediately after the copy of the current token. It's looking at the apostrophe D, and then it's copying that token and predicting that's going to come next. That's like the fundamental characteristic of an induction head. The particularly distinctive thing from a can we automate interpretability point of view is this stripe.
Right.
Where because you've got a long repeated sequence, there is just like this constant offset in the attention pattern between the current token and like where it highlights. I don't know why Mysterious is highlighting because and also thank. Weird. There's this like clear stripe, and you can just literally feed in the model like a batch of 100 sequences of 300 random tokens repeated, and then measure this induction stripe. I know, I recently ran a script across just like 40 open source models looking for induction heads by just looking for this stripe.
Right.
And it took like 5 minutes to run. And it's just like a very cute test.
And like maybe a little bit helpful to kind of position ourselves in that attention map matrix up there in the top left. The top right is our like causal masking. So that's why that's all empty.
Yep.
And then the diagonal is I'm attending to the current token.
Yep.
And so then anything to the left of it is I'm attending to a previous token. And so once we get to the bottom there, where the induction stripe appears, what's happening is this token that's at some offset down here is going back and looking however many tokens that paragraph is. Let's say it's 420 tokens, going 420 tokens back and looking at that one. And because we're copying, and then the next thing we want to copy is the next token, the next one is also going exactly 420 tokens back to pick something up. Fuzzily, as you pointed out with Mysterious, like there's some mysterious things going on in our attention here. So like it's a little fuzzy and you can see some like fuzziness on that line, but there is also this like strong off diagonal that says each token is attending a certain amount back in the context, which shows up here because we are repeating that paragraph exactly.
Yep. Yeah. Great explanation.
Okay.
Thanks for diving into that. One hypothesis I just thought of is the reason Mysterious is doing this mysterious thing is that it's reasonably easy to predict that the comma will come next just from like local understanding of the sequence. Models are really good at basic punctuation. So maybe it just has some spare capacity for looking a bit further afield. It's like, I'm going to have a comma next. I'm so confident in this, I can like afford to deviate a bit and like shove in a little bit of extra functionality into this induction head. No idea if that's true. But...
Yeah. Okay, the primary thing that's like extremely likely to happen is a comma. Let me look a little further afield just in case this is a weird piece of text where something bizarre is going to happen. So let me look at the last place a comma appeared in the context where you would expect a comma and make sure that nothing weird was going on around it. Yeah, that's plausible.
Makes sense. Yeah, it could also just be, I know, when you have repeated things, it would often be a single sentence that's repeated. And then when the end of the sentence happens, it stops being repeated. Maybe it's learned to be a bit more careful and like look a bit further.
Right.
I don't know. This is a little wild speculation.
Sure.
This is completely the flavor of mechanistic interpretability research.
Right.
Like, see something weird, you make guesses for why it's weird, and then you go and try to actually validate these and like figure out what experiments you'd run to tell the difference between the two.
Not dissimilar to debugging a complex system where you can't just reason from first principles. A distributed system, for example, where you have like limited observability, what you have to do is kind of like observe phenomena and then dive into them a little bit, form hypotheses, and then test those hypotheses.
Yep. So just drawing back to the graph, prefix matching score is the fraction of attention paid to that stripe.
Got it.
Where if it's perfect induction behavior, it's 1. If it's not doing any induction, it's basically 0, because if you're uniform across the attention and you're looking 100 tokens back, like 1%, it's basically nothing. And you see basically nothing to actually pretty good during the space change. There's also just like a really cute toy example of something I'm very excited about, which is automated interpretability and automating finding circuits.
Right.
Where you can just run this.
As with many things in automation, like the goal here is to find the lowest hanging automatable fruit and be like, okay, I can pull out, here's 30% of your model is doing induction heads. Don't worry about the mechanistic interpretability of those. We know stuff about that. If you're trying to find novel circuits, you can, to a certain extent, ignore those things and focus on the rest of it. And then as people add more and more automated interpretability schemes, you can focus more and more intensely on the parts that are hard to explain.
Yep. You can say, this could be done easily with a bigram. Models are good at bigrams, so I'm going to ignore this and look at the model's behavior above and beyond bigrams.
Right.
There's like another kind of table stakes in that flavor of interpretability. Here's the next graph, which is also really wild. To reiterate, here we're drawing deeply on this fact that 1-layer models cannot form induction heads, 2-layer models can, both in this toy attention only case and also if you add in MLPs, so it's a real transformer. And something that's super fascinating, this graph, the faint gray line is the 1-layer loss, the thick black line is the 2-layer loss. And these basically perfectly track each other until they diverge at this phase change. Like, I'm surprised they track each other so well up to this point. Because like the 2-layer model has twice as many non-embedding parameters. So scaling laws predicts it should do better. 2.5 billion tokens is quite a long time.
That's true. Yeah.
3 layers, similar effect. One random cute observation that this helped explain is in the original scaling laws paper, where they were looking at how model performance just depends on the number of parameters, not really on things like the number of layers versus how wide the layers are and things like that. They found this result that these scaling laws broke for 1-layer models but worked for 2-layer models.
Right.
And my guess is just this was just such a big difference for the loss that 1-layer models just couldn't cope.
Right. Yeah, this is maybe a fairly concrete example of why we need compositionality of neural network architectures. This is a circuit that, for the basic version of a transformer, cannot form in a single layer model and has this macroscopic impact on the loss. That is what the 101 deep learning class would predict, which is like we have to compose these simple modules in order to get the complex behaviors that we want, even though the universal function approximation theorem is in terms of like width of models. And there's at least some people who are like big on making models wider and wider and wider rather than deeper.
I don't know. I like to think that composition puts the deep in deep learning. So this is a cute example of kind of model debugging. Let's look at these 2 model snapshots before and after this big swerve and this big phase change. The fact that it's the PCA plot over here isn't significant. The important part is we're just choosing a model at the end and start of the phase change. And then for each token in this text, let's look at the log, the like per token what's, the log prob on that token. It's like, how good is the model at predicting that token? And red means gets better, blue means gets worse. What we see is that for these repeated strings, they're pretty red. The model's a lot better at predicting Dursley. Notes for people not familiar with the guts of language modeling, words get split up into tokens or subwords, and here space capital D, URS, and LEY are separate tokens, so the model gets points for each of those that it predicts. And it's allowed to use the D and the ers to figure out that Lee should come next. Also, I hate tokenization, and it's one of the worst parts about doing mechanistic interpretability research of language models, but that's a whole other.
Yeah. Still the messiest part of language modeling.
It's such a nightmare. Things that are repeated go up. This is super cute. This is like kind of debugging. So here it says misses, and it's like, oh, capital D comes next, when actually it's positive.
Right.
And it's kind of misfire.
So actually, so this chart shows the per token losses, which allows you to pick out, oh, here's this like bright blue thing. And then you can form this hypothesis that it's because misses is followed by Potter instead of capital D. What this chart isn't showing is what maybe the model's highest probability thing was, before and after. So I'm curious, do you happen to know for this particular example or for similar analyses like this, can you actually observe the thing that is being copied, that logit is going up at the same time as the correct one is going down? So that's like an even more fine-grained than this like per token loss.
I haven't actually checked, but if I was watching this and interested, you could figure this out by screwing around in a collab for about 10 minutes. Yeah, I'll put a link to my easy transformer library for mechanistic interpretability in the video description. And you can identify induction heads and you can look at the per token losses pretty easily. And there are some models supported that have a bunch of checkpoints. So you can look at these during training phenomena. A thing that I found pretty striking about interpretability is just how useful good interactive visualization tools are.
Yeah.
I would love to see someone make a version of this where you just hover over this and you get a pop-up telling you like what are the top 10 logits and their corresponding probability. Sorry, top 10 tokens and their probability, and then something which like compares that between the two models would be super interesting.
Right. If you write these visualizations in the right format, these are all things that you could, in principle, get merged into open source libraries for evaluating and monitoring models, right? Things like Hugging Face evaluations, data sets, et cetera, torch metrics, weights and biases, integrations into other libraries. There's like lots of places where people actually do want these kinds of generic tools readily available to apply to their models.
Oh, interesting. I've been making some tools like this. I'd love to chat about that offline. Anthropic released this library called PySfelt, which is a pretty good tool for making stuff like this. It's got some really janky internal machinery to hook up web dev code to Python code.
Man, every day I Google Rust GPU acceleration and Python WebAssembly every morning just to see when is the promised land coming.
Someone I'm mentoring is currently working on making PySfelt like a more functional and better maintained library, and I'm super excited to see what comes out of that. Here's another graph, pretty similar to what was being shown above. Oh, I think this does kind of answer your question.
Yeah.
This is how the ability to predict these changes versus the ability to predict Potter changes. So it's not quite Potter versus D.
Yeah, but it does at least state the model incorrectly predicts that the next token should be D. Like it's not a component of the visualization, but it is a component of the claim here. So that does answer it.
Yes. One thing which I find pretty striking is that as the induction heads happen, the model becomes really bad on Potter. This is worse than uniform.
Right.
But then kind of as training goes on, it becomes more moderate. Presumably this is because it's developing more sophisticated heuristics, like this is only a single repeated token rather than 5. So I should be less confident. And yeah, this goes from like basically uniform to very close to 0, which is just clearly something is happening.
Yeah. Actually, question, you mentioned uniform. So how many vocab elements are there? How many possible tokens?
So
is it 2 to the 12 or 3 to the 12?
So in GPT-2, it's 50,000. And what's log 50,000? Like 10.8. I don't know what we use for this model. Probably some custom internal Anthropic tokenizer. But I would be surprised if it's like dramatically different from 50,000.
Yeah.
So yeah, kind of uniform is about here. This is just briefly summarizing we haven't shown anything causal. This is all correlational.
Yeah.
But it's clearly waggling its eyebrows at us.
Right. This is already a NeurIPS paper, you know?
Yeah. And yeah, this is just pointing out like maybe it's a third factor. The fact that the score is pretty constant doesn't mean that what's going on with in-context learning is constant. It could be kind of shifting but maintaining this difference. Actually, you can't think of a metric like marginal difference in loss as being just some intrinsically meaningful thing. Because if a model has baseline 10 loss, so basically uniform, and you get 0.4 better, that's kind of incredibly easy. Learning a rule like full stops are followed by capital letters could easily get you more than 0.4. While if you're down to say 3 loss, which is roughly the correct token is always in your like top 30 tokens or something on average, then getting an increase of 0.4 is like really hard because all the low-hanging fruit has been plucked.
Right.
And the model's loss is improving throughout this entire period. So the fact that it's constant is actually kind of striking and weird, let alone the fact that it's about the same between these two models, even though the 3-layer one gets lower total loss in the second than the 2-layer one. This is just a really weird mystery. Maybe it's just the case that the models don't get any better at in-context learning and all of the other loss improvements just from a separate source. But you had a nice analogy on this earlier.
Oh, yeah. If I already have 8-bit and I add another bit to it, right? Like, it's important to recall that the loss here is an entropy, right? So our losses are measured in bits or nats. And these things are...
nats are just bits times log e over 2.
Right.
It's just the equivalent of a bit, but if your log is e rather than 2.
Right.
The same thing, just scale your axis.
Yeah. If I have 8 bits, I can represent 64 things. If I add 1 bit to that, I can now represent 64 times 2 things. So I've added 64 more things to my repertoire. If I have 16 bits and I add a bit, I don't get 64 more things. Yeah, if I add an additional bit, I get 16 bits worth of things to the 16. Yeah. Like, oh, I got an extra bit hides the fact that bits are already this like multiplicative thing. Getting 1 extra bit on top of already being able to represent 5 bits worth of the information in language, so apart from the like useful intuitions that you shared about like low hanging fruit and losses, just thinking about bits, we already have that phenomenon.
Agreed. Yeah, one intuition pop I find helpful is thinking about addition. So GPT-3 can add numbers, smaller models can't. Presumably doing addition is pretty difficult, though maybe it's just learning to predict entities and Fourier transforms. It's going to require like a lot more effort than just like an induction head. Sure, given that models get so big before they do it. But the lost benefit of being able to add numbers can't possibly be that high. It just doesn't come up that often. So clearly the effort to loss ratio has gotten pretty sparse by the time GPT-3 has learned to add numbers together.
Yeah.
One framing that I sometimes find helpful for thinking about cross-entropy loss and why it's a sensible metric is this kind of Bayesian framing, where if you think of what a model is doing as accumulating additional independent bits of evidence and adding them all together, if each shred of evidence adds 1 to the logits, then this is saying that each marginal bit of evidence should make us like twice as confident in our hypothesis. And the more confident we are, the like bigger a difference this makes, which is why kind of exponentiating when we get to a softmax is in some sense kind of principles.
Right.
And so maybe one thing that might be going on is that this in-context learning evidence of +4 nats for the correct token is kind of independent of everything else the model has learned. So you should just multiply them together, which is equivalent to adding in log space.
Right.
But I don't know. I consider this one of the pretty big unexplained mysteries of this paper that I'd love to see future work on.
Yeah. Relatedly, the reason why I think of the cross entropy as principled is that it transforms the like multiplicative updates that you would do in accumulating evidence in a Bayesian way into additive updates, right? Like if you're working in that log space. There's an N category cafe article about this actually. So there's an actual, like an honest to God, full and faithful functor here. So I buy that. In that light, thinking of this as like, this is a type of evidence that has a specific magnitude. I think that's a very promising way to maybe understand this.
But yeah, the fact that this holds for even much larger models is just wild.
Right.
Let's move on to argument 2.
Hold up. At about... Yeah. So we got about 10 minutes left. We could do another recording to cover more of the arguments.
I'm ready to mount another recording if you've got the time.
Yeah, great. This is a great stopping point, I would say, before we start another argument.
Seems good.